All right, so I guess let's get started here. Let me just make sure something strange just happened there. If you can put something in the chat to make sure you can see the screen. Do you see the presentation screen right now? Great, okay. The little green bar that's usually around the presentation just disappeared for some reason, so I wanted to make sure. Okay, so the way things lining up here. So this is the timeline of things. So we'll have today's lecture today. We're just going to wrap up important sampling, which we didn't get to last time, and just generally some course wrap-up stuff. And then there's no more labs, and so any more lab time that you normally devote to labs, you think of as final project time. Then there's Thanksgiving break this week, and then next week we'll have a lecture that is a final exam review. That there's an ICA that's already available, ICA MA, I'm sorry, ICA MB, and that is one that's due before that lecture. So that is sort of the collection of all the other Canvas activities from up until that lecture, for all the post-midterm Canvas activities. And so we're taking all those and they draw randomly from them. I think it's a 30 or 32.1. You can take it as many times as you want. And it's meant to be a final exam review that is fairly low stakes. And so you can take it if you like. If you don't like, we drop several of these Canvas activities and it'll drop the ones that best benefit you. But it's meant to motivate you to bring questions to Tuesday's lecture period. Once Tuesday's lecture period starts, then it goes away and then just practice forms come into play. ICA MA is the practice exam for all of the questions from before the midterm, and ICA MB is the one for the practice questions for everything after the midterm. So together, they're kind of a cumulative practice assignment that you can work on working towards that final exam. So feel free to come with questions on Tuesday. So Tuesday after Thanksgiving is meant to be a kind of a review session. And then Wednesday after that, there are these project presentations that are due, a 10-minute video you upload to Canvas, as well as a 4-page project report. And then you'll be done with your side of generating this presentation material, this project material. So then all that's left then is that by Saturday, you have to do peer reviews of one other presentation and one other report. And so those will automatically get assigned Wednesday night, who has to peer review what. You won't, I guess it's possible that you'll be giving a peer review to the same group's presentation and report, but in general, there'll be a different presentation and a different report. There's a rubric for both of those, and so you'll fill out a rubric, so giving them numerical scores, following the instructions online, and then you'll also put, at least a few sentences of constructive feedback. All of that will be anonymous to the presenters, and so you'll be giving them anonymous feedback on that, and then I will use the numerical scores and your comments to help form my grade that I will give the project reports and the project presentations. And then also I will give everyone credit for giving their peer review. So as long as I see that you gave a constructive peer review, then you'll get credit for that peer review, which is a fraction of your individual final project score. And then we'll have the final exam. This is the standard way we do the final exams, but this final exam schedule or structure here is a little bit different. So I guess I could, this here is not exactly, doesn't work exactly this way this semester. So this semester, basically the Thursday of the last week of class, you do get this exam 1. This will be the individual one where you're going to get 90 minutes anytime that day to take it with lockdown browser, with monitor. And then the Friday after that, you get to take the exact same exam, but you can take it collaboratively with your peers in the class and open notes and open book without lockdown browser. The first exam will be 80% of your exam score. The second exam will be 20% of your exam score. If you don't want to take them Thursday and Friday of the last week of classes, then there is a process on Canvas where you can go into the people section on Canvas. And then from there, you can go to groups and you can move yourself into the later exam group. And the later exam group will get the exact same 2 exams, but instead of being Thursday, Friday, they'll be Monday, Tuesday of the original finals week. So you can be free to do that. You can also be free to see who else is in that group so that you know who you can collaborate with on that Tuesday collaborative exam. So that's the way things are kind of structured there. So with that in mind, let me clear and then I'll show the question slide here. So are there any questions about the way things are rolling forward, about the timeline moving forward, projects and exams?
Yeah, sorry, could you just repeat which day we need to decide if we're going to do the late final or the early final?
Oh yeah, so December 1st is when you should decide on that. So by December 1st. So, and then on that, at the end of that day, I'm going to go into those groups that are on Canvas and I will convert them into virtual sections. And then that will allow me to assign one section a certain final exam, the other section another final exam. So if you'd like to take it late, hopefully you'll be able to decide that by December 1st. My hope was that by then you'll know everyone else's final exam schedule. And so this is primarily motivated by, I don't want you to have like 6 final exams on Thursday and 4 final exams on Friday. And so I know it's pretty compact. I believe I can, as long as I give you the opportunity to get all graded work in by that last week of class, I'm okay. That's why I'm giving you, everyone by default is on Thursday, Friday, but if you need it, you can go to Monday, Tuesday. I don't actually know for sure if that's the letter of the law. And so if they find out I'm doing that, they might tell me, no, you really have to do everything by that you can't bleed into Innovation Week. But I'm just hoping that they'll, that they won't find out, or that there will be so few students that choose that it won't be a problem anyway. So try to make your selections by December 1st. If you have any questions about this, just feel free to send me an email. Any other questions? Oh, I'm sorry. About what percent of the final, what I say is old material versus new material? There's a question there. That's we can go over that a little bit on Tuesday and during the final exam review. But you know, so I mean, I still have to write the exams. I don't know exactly what percent is which. I can tell you that I mean, I view a lot of the stuff we've done after the midterm as building on the stuff from before the midterm. There's some things that, you know, like you're probably gonna have to do a hand simulation or at least some aspect of hand simulation on the final exam. So there's some things that we haven't really done since the midterm that you probably still will have to do, but you know, like the chi-squared test, we've just modified the chi-squared test. And so I'm not going to ask you to do a chi-squared test from before the midterm and a chi-squared test from after the midterm. So there's some overlap there. So it's hard for me to give you a quantitative number. Certainly things are going to be more biased towards the end of the class. So I would say there's a larger fraction should hopefully come from the end of the class because that's, you know, it's the more developed content. I do think I put at least one example final exam from previous semesters online. On Canvas. I would recommend scrolling through that and you'll get kind of a feel for how I like to balance things. The one from last fall was not a Canvas exam, but it was a Scantron exam. So it will share a lot of the aspects of the kind of auto-graded feel of it. And so that might be a nice model for you to think about these things. Any other questions about this? Okay. I also, just as a hint, since it's got it up here, is there are the course evaluations for all the engineering courses are there. So those I think are available until December 4th. And so if you'd like to leave a course evaluation, then of course we always like to get that feedback. So do our bosses like to know how well you think of our teaching. So you can feel free to fill that out, but I think it disappears December 4th before the original finals week or something. Okay, so let's move on. All right. All right, so let's do a quick attendance exercise. So I will put the URL in the chat as usual. And the question you can see up here on the screen, and the question just is, what is the ultimate goal of VRT in simulation studies? So what is the point? Why are we doing VRT? So that's what I just want you to sort of get locked onto now. So go ahead and fill out your answer to that. And does anybody have a response to that? What is the point? Why are we doing variance reduction techniques in simulations? Why not just leave the variance as it is? Anybody brave enough to give me a guess? It's not a hard question, or it's not a hard answer. It's not a technical answer. It's sort of an economical answer. Anybody? I can wait. Well, no, I mean, so it's not, so there's a question, is it to create more realistic, accurate models? Variance reduction techniques aren't, we're trying to get a better understanding of the way inputs affect outputs. And so in some ways, we're trying to, I guess, build more realistic kind of statistical models. But the variance reduction techniques, there's a more practical reason why we do them. Because I mean, we don't have to do variance reduction. We can, yeah, so then there's another comment there, to have more precise confidence intervals, right? So that's half of it. So we do variance reduction techniques to have more precise confidence intervals. I like that, but there's other ways we could do that. So we can get tighter confidence intervals without using variance reduction techniques. And so, so what is the point? Why do you use variance reduction techniques as opposed to the other way? So I guess I could say, what is the other way we could get tighter confidence intervals on our inferences? If we don't use variance reduction techniques, how do we compress our confidence intervals? We use, yeah, so the replications. So normally we would just dial up the replications. So we run 100 replications, we get a confidence interval that's this big, and we say we really wanted a confidence interval that's this big. Well, normally you would say, okay, instead of 100 replications, I'll run 1,000 replications. But 1,000 replications of a simulation might mean going from an hour of runtime to 24 hours of runtime if it's a really complex simulation. So variance reduction techniques help us reduce the number of replications. And so that's kind of the big point of VRTs, is how do I reduce variance in my simulation outcome so that I can use fewer replications? I get the same quality results without running as many replications. Because like that call center was, I think, the first simulation that you guys have simulated that really kind of took a while for those replications to run. So is there a way that I can run, if I want to compare one call center to another, when I compare them to each other, is there a way that I can guarantee that I only have to run 100? I don't have to do the 1,000 that I made you do to generate that histogram. So that's really what we're trying to do. And the fundamental mechanism that we're using to do it is by controlling or accounting for sources of extra variance. And so the idea is we love variance because variance shows us difference. We know that we have call center 1 and call center 2. There is a true difference between call center 1 and call center 2. That is a source of variance. So whatever we changed from call center 1 to call center 2, like, cross training, we did cross training in one but not in the other. That change is a source of variance. So the degree of cross training generates variance in the output. Now, in order for us to really hone in on to decide, what is the true effect of cross training and not the effect of other things, we would like to control for those other sources of variance. And so normally we're controlling for variance that just comes from differences on our inputs. So if we know something about our inputs, we can subtract those away so that any difference left in the output is truly due to a difference in the systems. And that's what we're kind of doing here. And we introduced, so I got through 3 of these, but we talk about 4 of them total. And I'm going to talk about importance sampling, the one we missed last time today. And there are these 4 basic ones that we talk about in 475, and common random numbers, which is the only one here for, well, I guess the CRN or control variates also, but this is the one that really is for relative performance estimates. And so I'm comparing 2 call centers, and so I pair up their random numbers. And so I'll give kind of a cartoon version of that in a second. Antithetic variates, which are kind of like the version of common random numbers, but it's focused on a single model, or I'm interested in the absolute performance estimation. Then importance sampling, which is another way to do absolute performance estimation. This is the one I didn't get to before, but I will cover today. And then control variates. And control variates is the one that you can actually apply to real world experiments too. They don't have to be simulation models. These here, we are using the fact that we are the masters of randomness. So we can configure the random number generators. And so we can actually then set up these 3 different types of VRTs. This VRT down here, control variates, you can apply that to any experiment you do. So if you're testing a jet engine, for example, and you want to control for the effect of temperature in the test rig on the jet engine's performance, well, you can use control variates in your real experiment with your real jet engine. You can do that just as well. So let's do some review of that and then introduce the importance sampling. Good, again, just making it clear, the key point here is that we are trying to reduce variance so that we can run fewer numbers of replications. So the kind of key, the simplest example of that are these common random numbers, CRNs, where we are going to have 2 simulation models. So you can think of simulation model A up here. This is like our call center with no cross training, and simulation model B is like our call center with cross training. And we have the same random number seed goes into each replication. So if we seed a replication of this, that's going to set up a string of random numbers that you can think of as like the inter-arrival times between callers. So for a single replication is seeded with a single random number, I get a string of callers. And so it's like I'm running the same callers into call center A as I am into call center B. That's effectively what I'm doing with my with common random numbers. Call center A will give me a performance measure. This will be, for all of these callers, this was my average wait time, for example. Call center B will give me that same performance measure. For those same callers, if they, hypothetically speaking, would have called in to the other call center, I would have gotten this performance measure down here instead. And I can take these paired outputs. They're paired because I ran the same callers into both of them. They, in some ways, are dependent upon each other. So there is a reason to believe that there is a statistical correlation between the output here in A and the output here in B. And if I subtract those, I get a difference. And that is a difference in performance for these callers. So in a world where I got these callers, this day of data, then I measured performance twice, one with simulation model A, one with simulation model B, and then I took the subtraction and I said, for these callers, this is the effect of simulation model A over simulation model B. So in this particular case, let's say I want lower is better. Let's say I want wait time. Then what we're saying is that for this set of callers, simulation model B happens to be better. And how much better it is, it's better by 2.1 minutes if these are minutes of waiting time. But that's only for one replication. So that's only for one string of callers. So I need to do that for another string of callers, another string of callers, to see how general this result is. Because it might just be that this one string of callers just happened to be a string of callers that was really well suited for simulation model B and poorly suited for A. But a more generic string of callers is going to flip things around. So most of the time, maybe A is better. It's just I got lucky, and in this particular time, B was better. So, so what we do then is we try a different random number seed. So here I got a different random number seed going into both simulations for replication 2, and that gave me a different string of callers. That different string of callers gave me a different performance measure for A and a different performance measure for B. And lo and behold, for this string of callers, then it turns out that the order flipped. So now A is better for this string of callers and B is worse. And so that's why I got a negative number now for this difference. So replication 2 had a negative number, meaning that now A was better and not B. So I can do that over and over and over again. So I just run a bunch of different random number seeds. And so every replication is a different seed going into both simultaneously. And then I measure a difference. And these differences are independent from each other. And so I then can use a paired difference t-test to test to see whether this set of differences, which are all, again, independent from each other. So there's independence, there's no correlation from one row to another. So I can now use a one sample t-test or a paired difference t-test to test whether this set of differences, if it's basically, I'm looking for a confidence interval. So I take this and I generate a confidence interval, and that confidence interval is going to have some mean difference. And so we'll call this d bar. And then it has some half width. So it's in plus the half width here. And then it's going to be minus the half width over here. And then the question is 0 in this interval? That's what I'm asking here. Is it in the interval? And if 0 is in the interval, then that means that we can't tell the difference between these two simulation models, at least for this number of replications. We increase the number of replications, maybe we'll be able to see. If 0 is not in the interval, then we have detected a difference between these. And A might be better than B, or B might be better than A, depending on whether 0 is to the left of the confidence interval or 0 is to the right of the confidence interval. And that's CRNs. Are there any questions about CRNs? Is that pretty clear? What we mean by common random numbers? Okay. And we can do CRNs in Arena. Arena's got this great way where you can go into random number streams and set them to common. And what that does is it ensures that replication 1 is always going to use a seed of 100,000, replication 2 is always going to use a seed of 200,000, and so on and so forth. So if you have multiple simulation models that you just opened up independently in Arena, but they all are configured for common, then they'll all use the same seed value for replication 1, replication 2, and so on, so that then you can pair up their outputs and do a similar table as I've shown here. Okay. So then the flip side of that for absolute performance estimation is when I have a single simulation model. And then it's like, is there an analog to common random numbers when I'm not trying to compare two simulation models, when I'm just trying to make my estimates of one simulation model better? And the idea here is I take a single simulation model and I generate pairs. And so those pairs are a simulation model with an odd replication number, and then a simulation model with, say, an even replication number. So I always run, replication 1, then replication 2, replication 3, then replication 4. And the odd numbered replications always get a fresh set of random numbers. And so I run, pardon me, I'm sorry, my throat is really dry this morning. I run the same random number seed, so seed 54. I run it to generate a set of random numbers. And those random numbers, again, you can think of them as inter-arrival times between callers in a call center. And I run them into my simulation A, and I get some performance measure. And then instead of generating a new random number seed, I just take all of these numbers, which, again, these are just numbers between 0 and 1. And I take their complement. I do 1 minus them. And so 0.25 becomes 0.75, 0.8 becomes 0.2, and so on. And so these here are a complementary set of random numbers that are paired to the set of random numbers that I generated in this first replication. So I'm generating another replication that's going to have a unique output, but it has an interesting relationship in that the random numbers that went into it are 1 minus the random numbers that went into the previous replication. And doing so, we do that in the hope that we create a negative correlation between these two, where if this was a bad result up here, then we're hoping that this will be a good result down here. So if we got a bad set of callers here for this particular simulation model, then we're hoping to get a good set of callers here for this particular simulation model. And if we can get co-located good performance measures next to bad performance measures, then in very few replications, we run the whole gambit of performances. And so in fewer replications, we get a more representative sample of all the things that can go right and all the things that can go wrong. And that allows us to use fewer replications to get a tighter estimation of performance from a single simulation model. So that's what we're doing here with the antithetic variates. And so what I've got animated here is this is what's for random for one seed. And so my next step is to then choose a different seed, and that different seed gives me a different set of callers to go into one model. And then I do 1 minus those to give me callers to go back into that model. And for each one of these, what I'm going to do is I'm going to take their performance measure for one, and I'm going to take the performance measure for the other. And instead of subtracting them, like I did in common random numbers, I'm going to take their average. And so that's what I do here. And so this here is the antithetic variate, which is just the average of each one of these random number pairs. And so that's what I'm doing right here. And so I'm going to take each one of those antithetic variates, and I'm going to put them into a table, just like I did with common random numbers, and then use that to generate that confidence interval that I can use to estimate the absolute performance of this single simulation model. So let's see what that looks like. Here's, you could imagine 100 replications. Each one of them is associated with their different seed. And so when I say replication, realize that what I really mean is one independent replication, and then a kind of dependent replication that follows it, and then the average of those two. And that's what ends up going in here. That's an average. So this is like replication 1 and replication 2. This is like replication 3 and replication 4. And then this here is the average from each one of those pairs. And so I can take each one of those and I can form a confidence interval that'll hopefully be very tight, where it will have some average, and then it'll have a half width over here and a negative half width over here. And because I'm not doing a relative performance estimate, then I'm not comparing to 0, I'm comparing to whatever my hypothesis is. And so if I say, I want to see, is this, the output of this simulation, is it at least, is it greater than 5? Well, then in that case, I'd say, well, where is 5 with respect to this confidence interval? And if this confidence interval is strictly greater than 5, then that means that I can conclude that my simulation model performs at least as good as 5. So, so that's really the question here. And so the antithetic variates help us squeeze the size of this confidence interval down so that we can reject more hypotheses, so we have more sensitivity. And that's antithetic variates. So the variate term refers to each one of these averages. So there are questions about that, about antithetic variates, how it's kind of the absolute performance version of common random numbers.
So this is the one where we're looking for a negative correlation, right?
That's right. So in common random numbers, you hope for you're generating positive correlations, hopefully. And in antithetic variates, you're hopefully generating negative correlations.
Okay, perfect. Thank you.
And if you don't, so if in common random numbers you actually generate negative correlations, common random numbers will be a bad thing to do. And antithetic variates, if you generate positive correlations, then it'll also be a bad thing to do. So that's why in both common random numbers and antithetic variates, you really have to do a pilot study of a small number of replications just to see if you've managed to reduce the variance relative to what you'd expect if you did things in the independent case. And if it tends to be that independent replications give you a lower variance, you should use independent replications instead. So for all of these, you run a pilot study, and then you look for, and then the question ends up being, does the independent case where you forget about all this give me lower variance, or does this method give me lower variance? And so which one has lower variance? And go with the one that has the lower variance. So what I mean by that is, like in common random numbers, you can calculate the variance for the simulation separately and add those together. And then you can also calculate the variance for the differences between them. And if the variance in the two together, added together, is larger than the variance of the differences, then that's a good thing. But if you add the two variances together from the two different simulations, and that's smaller than the variance of their differences, then don't do common random numbers. Just do a 2-sample t-test. So just do it, treat them, but I mean, run them independently. You don't use those data because those data are not independent because you ran the same random number seeds into both. So that's kind of the question, is when do I decide to pair up my outputs versus leave them unpaired and running independently? And you just have to run kind of a pilot study to see if it's a good thing to do that. Same thing with antithetic variates. All right. So questions of that? All right. So now I want to jump into a different, what we didn't get to last time, but it is an important topic, important sampling. And so, as you know from other classes, it is impossible to completely engineer away all failure. What we can do, hopefully, is make failure rare. And we can even control how rare that might be. So you might have, the whole point of Six Sigma is, well, okay, so there's two visions on Six Sigma, right? So if you're saying Six Sigma could be a vision for very high quality manufacturing. So we are going to make sure that there are very few duds that come off the manufacturing line. And what we mean by very few is, it's in the tails of the distribution. It's way out past Six Sigma, so very, very few outputs will be these bad outputs. Now that's one way to view Six Sigma. You can also view Six Sigma as criteria for how far you have to go before you can stop improving quality. So of course we pitch Six Sigma as a way to say this is for high quality production, for high quality manufacturing, but it's also kind of for low quality. I mean, if I had a way to generate 8 Sigma, then a Six Sigma black belt would tell me, well, why are you spending money on 8 Sigma when you can do 6 Sigma instead? So there's this question of how bad are things, and do I really want to make them better? So do I need to put effort into making them better, or are they good enough where they are? And so it is really important to be able to estimate exactly how rare these rare events are. So, but the problem is, it's hard to estimate rare events. So, because they're rare. I mean, that's the whole point of it. Like in the terms of, in terms of simulation, if we've got a high fidelity simulation of a system, and things like let's say it's a nuclear power plant. Well, if the nuclear power plant only goes into a critical meltdown once every 1,000 years, then we may never see a simulated meltdown in 1,000,000 runs of our simulation of that nuclear power plant, depending on kind of time scale of things. So how do we actually know that our 1 out of every 1,000 is correct? It might be 1 out of every 10,000, or it might be 1 out of every 500. If our spec is 1 out of 1,000 and it's actually 1 out of 500, it might still be very rare for us to see the 1 out of 500. But, and so we might incorrectly conclude that it is rare enough when in fact it happens too frequently. So estimating how frequent rare events happen is really important. And it can be, I mean, if you look at, for example, product recalls, then you kind of see really how important it is to get these estimates right. So Samsung, it seems like every other year, Samsung has a problem with their products, that something goes terribly wrong with one of their products. It's rare, but they sell so many of them that the rare product ends up doing terrible things. And so, like, for example, this happened not that long ago. This is a Samsung top-loading washer. If you or your family members have a Samsung top-loading washer, if you look at it, you probably will notice a lot of similarities. This is a fairly recent event. And what they found was with this Samsung top-loading washer is that in a small number of cases, if you put bedding in the washer and it rotated a little too quickly, it would generate such harmful vibrations that the drum here would come loose and would go flying out of the washer and would end up hitting things like, in this case, it popped the top off and hit the wall and put this giant hole in the wall. People, from what I understand, were actually injured by these because they came in to see, well, what's all the noise that's going on in my laundry room? Suddenly this thing pops out and hits someone. So this is a critical error made due to poor engineering. And if they, and even if they got their rare event, like they said, well, this isn't going to happen that much. The thing is, the PR they got off of this was just horrible. And so I'll get rid of this this pen. So they become known for this error, and they had to recall a huge number of washing machines, make fixes to them. They had to, give people this. This was really, really costly to Samsung, and so knowing how rare this is, and then trying to then predict, even if it is really rare, if it happens frequently enough to get into the public press, like probably most of these washing machines were fine, and it really was super rare, but because it got amplified, then it caused them even more problems than the actual faulty machines themselves. And again, Samsung goes through a lot of this. And so, later than that, some of you might remember that their Samsung Galaxy phones, that a Samsung Note 7, that they had these crappy batteries that they put in them. And these batteries would just catch fire in people's pockets. And it was pretty dramatic. These were very, very rare events. But figuring out how rare they are tells you if you really need to go back to the drawing board to bring this down, or if gives you a better idea of how you're going to have to manage this risk once it's unleashed on the world. And I don't want to only pick on Samsung here, as much as I enjoy that. There are plenty of other cases. So in the news today, Boeing, is finally, so this, now from, I think, last year, this particular set of images that I've got up here, and just, I think, today, they are now finally getting to the point where they can start putting these planes back into the air, this 737 MAX 8. And that was, again, from not understanding how rare a particular rare event was. And so engineers always have to decide at what point do you release something that has a chance of going terribly wrong. And so being able to estimate how often, or what that chance is so important to when you're deciding when to release this product onto the world. And you find out that when Boeing was evaluating this plane, if you look at quotes from people there, they were evaluating them in simulation. And so they, so this is some quotes here, and they say this particular pilot, Mark Fortner, played a central role in the development of the plane, complained that the system was acting unpredictably in a flight simulator, running rampant. So this is an example where in the simulators, they actually did have the ability to estimate how frequently this particular rare event was. And it happened frequently enough in the simulator that they, apparently should have taken it more seriously. So when you notice weird things happening in simulation, you should investigate them. And one of the ways to investigate them is to try to induce those rare events to happen more frequently so that you can better investigate what's going on in those rare events, and then better investigate exactly how often these rare events really will occur. And that's what we're talking about here, is how to make that happen in a simulation. So, so basically what I'm saying here is that rare events are important. Estimating the frequency of catastrophic events is ideally done in simulation. You don't want to actually have a nuclear meltdown to estimate how frequently nuclear meltdowns happen. But how do we trust our estimates without building huge, huge, huge numbers of replications? If it only happens in one in every 1 million runs of your simulation, then does that mean you have to run 100 million runs of your simulation to get a good estimate of how frequently it happens? So what we're going to do, or what we do in importance sampling, is we look at our input models. And what we speculate is that the rare event that occurs because our input models happen to generate almost pathological cases. So we happen to get a string of customers that just overstresses our system more than the normal set of customers. And so if this is the distribution of things, like this is the distribution of inter-arrival times, for example, this is a standardized score of the differences in the standard, the average inter-arrival time, is that there are maybe a group of inputs, a group of inter-arrival times that are just so bad that they can cause problems. And so what we're going to try to do is take our normal input model and find a way to focus just on these events, and then simulate only these terrible input events, and then find a way to then take our outputs and rescale them so that we're back into a normal world where we can make sense of our results in this bizarro, terrible world relative to the actual frequencies we see in the real world. So let me kind of elaborate a bit here. So the idea here is that I have my normal input model, and notice it's centered here on 0. So this is like a standardized score of my normal input. And so I would normally generate all of these outcomes here. Now, I would just like to focus on these outcomes that are up here. So they are, their average is more like 2.5 rather than 0. So I am going to effectively use loaded dice. So I've got fair dice that went into my original input model, and now I'm going to use loaded dice that go into this model here. So I am going to force results that normally happen rarely to come out of my input models. So by doing that, I can then use the known amount of overrepresentation in my input model to rescale the distribution of the outputs that I get. So in other words, in this input model here, I'm going to have rare, it's rare that I'll have bad outputs. So the outputs that I'm interested in are going to happen very rarely in the normal case. But over on the right-hand side of the screen, when I use pathological inputs that are just stressing to the system, these are not normal inputs. If I overrepresent them so that I am in a bizarro universe where these terrible inputs happen all the time, in that case, I'm going to get common outputs that are bad. So now I'm going to get common bad outputs. And if I'm interested in, so in this bizarro world, then the bad output, so the plane crash, for example, the plane crash happens 100% of the time in my bizarro simulation world. Now, the question is, well, then how do I make use of that? How do I estimate how often it's going to happen back in the real world? By building a bizarro world, I don't need to use that many simulations to find these bad outputs. So now I can maybe generate 100 replications, and on 95 of them, I'm going to get the bad outputs. The question is, how do I then rescale that 95 out of 100 back into my real world to find out, well, if in the bizarro world it happens 95% of the time, how often does it happen in the real world? In the real world, it might only happen 0.00095% of the time. So how do I do that scaling? And it turns out that I can use what's called a likelihood ratio to do that. So basically what, and I'll show you an example of this, I am going to be able to divide the PDF from my normal input model by my bizarro PDF of my bizarro input model. And this is going to give me a ratio that allows me to scale the overrepresented fraction in the bizarro world into the normal world fraction, which will be much, much smaller. But it allows me to effectively estimate a small quantity in the real world by only using a small number of replications in the bizarro world. That's what we do in importance sampling. So let's see an example of that, because I'm sure it seems very abstract right now. So imagine I have, this is one simulation model. So this is an absolute performance measure case here. And I generate R replications, so 1,000 replications or whatever. And so each replication's got a different string of random numbers that's going into it. So this string of random numbers goes into the simulation, generates this performance measure. In another replication, another string of random numbers generates another performance measure, and so on. So I get a bunch of performance measures out. Now, by definition, nearly all of my outputs are typical. I don't see any one of these catastrophic failures in my outputs. If I want to see one of these catastrophic failures, I might need to go from running 1,000 replications to running 1,000,000 replications. And even then, I only see 2 or 3 of my really catastrophic outputs. And so the confidence interval on that proportion will be very high. So what I'd like to do is choose input values, so choose random number seeds that we know are going to stress my system to the point where we think they will generate more of these pathological output cases. So I've now generated the same R replications, but now I've used an input model that it always is in kind of a pathological range. So if these are inter-arrival times between customers, now my customers are always arriving in like bursty levels. I'm always getting one customer that is arriving right after the other customer. And so I end up getting huge lines that are out the doors, because in this world, then it just ends up being that I get really bad luck and customers all arrive at once, for example. So I run all those in, and then I end up getting, some normal values, some typical values of my outputs, but most of my outputs are in these ugly ranges. So finally, I get a lot of these really bad outputs. And so you can view these as times where a customer had to wait longer than 10 minutes. And so I would like to estimate how long would a customer have to wait more than 10 minutes? Well, in the normal simulation, I would have to run lots and lots of simulations to get even a few of those. Here, I'm in a bizarro world where customers always wait longer than 10 minutes, or almost always. And I can use the fraction of how long they wait longer than 10 minutes in the bizarro world to then figure out how long they wait longer than 10 minutes in the real world. So what I'm going to do then is I am going to then look at all these interesting outputs, and I am going to then put those into a table here. And I'm going to say that these are my pathological outputs. And then I am going to categorize them as, are they an interesting failure case, or are they a normal case? And so I'm just going to give them ones or zeros. And so the average of this column here is the proportion of time in the bizarro world where we get a failure case, where we get a failure mode or an interesting case. And so that will end up being a very large number. Now, what I can do is I can take each one of these ones and zeros and I can scale them by what we call a likelihood ratio. And that likelihood ratio will be the PDF of my input string in the real world divided by the PDF of the input string in the bizarro world. And those two things will then scale whatever my output was, 1 or 0, in my bizarro world, so that it scales down the fraction, so that the average of this column will end up being the actual ratio, or the actual number of times I see these interesting cases in the real world. So that's what we're doing here, is we are creating a scaling counts from the bizarro world, so that instead of being ones and zeros, they're going to be like 0.05s and zeros. So this down here, again, this is a likelihood ratio. And so I could just try to write that with my mouse here, likelihood ratio. And that likelihood ratio is got where I've got F is the input model. So it's just a PDF of all of the outputs, or all of the inputs going into the real world. And then G is our, I'll call it our amplified model or something like that. And so this is the pathological case where we are getting only bad luck. So we've got our normal, like our nominal luck model F, and our bad luck model G. And if we look at a particular outcome, so you can look at you can say, okay, in my Bizarro world, I got a tiny interarrival time followed by a tiny interarrival time followed by a tiny interarrival time, and so on and so forth. And I can look at that string of interarrival times. And given that I know that all the interarrival times are independent, I can then say, all right, what's the probability that I would have gotten that string of terrible interarrival times in my real input model? Well, that's just going to be the, say, exponential, if they're exponentially weighted, that's going to be the exponential probability of the first interarrival times the exponential probability of the second interarrival, and so on and so forth. That'll give me a very, very tiny probability density that will be my F case. And then in the G case, I take my modified model, which has been shifted so that it generates lots of these ugly cases. And then I say, well, then what is the probability density that corresponds to this exact same string in the Bizarro world? And that will be a larger number. So my F number is always going to be smaller than my G number. And so this likelihood ratio, this ratio of densities, is going to scale any positive count, 1, down, so that this fraction that I estimate from this column will end up being much smaller than this fraction that I estimate from this column. And I can do a confidence interval around that fraction, so this is like a quantile estimate if I want to, and I can use very, very fewer replications to generate high confidences of these fractions here, even though they're very rare events. So that's what we do with importance sampling. We generate pathological inputs that make it easier for us to estimate how frequently infrequent events happen. So are there questions about that? That was the new topic that I wanted to make sure we got covered. It's another important variance reduction technique. And in this case, the variance that it's reducing is we're actually taking very variable outputs where sometimes they're typical and sometimes they're terrible, sometimes they're terrible in other ways, and we are reducing variance by creating a simulation that only focuses on the bad cases. And so it will have low variance and allow us to get a high estimate with very few replications. But then the trick then is we have to then convert it back to a world where we would have had high variance in the inputs. And so that's what this likelihood ratio scaling is all about. So, and I'm not gonna, I doubt any of you will use importance sampling for your final projects or anything like that, but it's an important term that you should know as you go into statistics in general, but then just more specifically simulation modeling, because it's a common tactic in simulation modeling. Okay. No questions. And I'm sure that seems a bit abstract. Okay. All right, so the last thing that we covered last time that we did have a chance to get through is control variates. And I just, to be fair to all the rest of them, I just want to give a little quick cartoon overview of control variates. So in control variates, we're focusing, let's say here on a relative performance case, but control variates can be used in relative and absolute estimation, and they don't have anything to do with simulation specifically. Control variates are a way that you can control variance in any experiment that you design, whether it be with a real physical system, like a real factory, a real jet engine, a real grocery store, or whatever, or in simulation. And they are strongly related to things like generalized linear mixed modeling. And so if you go into a more advanced statistics course where you talk about kind of generalizations of the linear interpolation that you've seen already, linear models that you've seen already, then this is sort of very much related to the multivariate case of those generalizations. And so the idea here is, I did not mean to black the screen. I apologize for that. Let's go back. So the idea here is I've got an important, so I'm trying to estimate the output of two different simulation models, simulation model A and simulation model B. And there is an input that I can send in to both of these that is easy to control. So, you know, in the case of common random numbers, maybe I can control the common random numbers that are going into both of these. But there is some element of these two simulations, the randomness between these two simulations that I can't easily control. So and you can view this as in some of my input models, I can use common random numbers, but in other, I might actually have real data going into simulation A from the real world and real data going into simulation B from the real world. And I can't control these. So these might be real temperature data, for example. And so these are actual temperature data taken from a real world, wherever simulation model A is going to go. And this here is real world temperature data taken from a location where real world simulation model B is going to go. And I can't control the temperature for each replication of these models. I can maybe control the power demanded if this is a simulation of a power generation model. But so this is maybe how much it has to supply that day. But I don't know these variations in temperature or something like that. So I look at the output here, and I know that the variation in this output is in part due to the variation from just this being a different simulation model than this. But some of that variation is due to the variance I get from the uncontrolled inputs, from the inputs that I can just measure. So I would like to subtract out the variance from these inputs that I can just measure. And that's what I'm going to do here with control variance. So what I'm going to do is I'm going to basically figure out that for this input, what is the average across all of my replications? And then from there, for each replication, I can then say, how different is this value from the average? And how different is this value from the average? And I can use those differences to then adjust my performance measures so that I effectively am subtracting off the amount of variance that is due just to this variable and not due to fundamental differences between the simulations. So that's what we're going to try to do here. Now for the absolute performance case, where I've got one single simulation model, it's very similar. So in the absolute performance case, I've got simulation model A, and I'm just trying to estimate a better guess at its absolute performance. And I've got samples of an input model. So you can think of these as inter-arrival times from, generated randomly from ARENA. That's one example to think of that. Or these could be real data from a real system. And the idea is across all of my independent replications, then I've got different strings of arrivals. So I've got this string of arrivals. So these two customers were separated by 1.4 minutes, these by about 7 minutes, these about 3.4, and so on. So I've got a string of arrivals here, a string of arrivals down here. Now I can calculate that for this replication, the average inter-arrival was 2.3. And for this replication, the average inter-arrival was 6.15. Across all of my replications, I might figure out that the average was 5. So in other words, for this replication and this replication, they're going to vary, but they're all going to vary around 5. So I know that on average, I get, I might have designed this system so that I have an average inter-arrival time of 5. But just by random chance, these 100 arrivals happen to have an inter-arrival time that was lower than average. And these down here happen to have an inter-arrival time that was greater than average. And so I would like to see what component of my output here is just due to the fact that these inter-arrivals are just happen to be unluckily less than average interarrival times, and these just happen to be luckily greater than average interarrival times. So I am going to, there's some variance between these. So, 10.1 to 17.5, there's like a 7.4 difference here. And so my question is, what fraction of this 7.4 difference is just due to the fact that these inputs have a different difference? And if I can subtract off that, then I can subtract off the effect of interarrival times so that I can just focus on the effect of something else. Like maybe I don't really care so much about how interarrival times affect performance. Maybe what I really care about is how variation in service affects performance. Well, this allows me to divide out the variance contributed by interarrival times to the variance contributed by service times. That's what I'm trying to do here. So what I do here, and this is just, I'm just summarizing, just by chance, some are easier. How much of the variance comes from that output there? Can we use that information to reduce that? So what I'm going to do for this absolute performance case is I'm going to generate a measurement. I know my average interarrival time, my desired average interarrival time across all the replications. And then for this replication, I know its average interarrival time. So I can calculate how much better or worse this replication is relative to the average case where everybody arrives at exactly the average interarrival time. And that's going to calculate some difference here. That might be positive or it might be negative. And I'm going to take that difference and I'm going to scale it by some quantity that I have to figure out, a good choice for that. And then I'm going to subtract that scaled difference from the measured output for this replication. And that will give me a new output for this replication. I know that if I take the expected value of this estimator, so if I take the expected value of this Z, if I push that expected value through, because expected value is linear, then what I'll find is that all of this extra contribution is going to drop out, and the expected value of my Z estimator will be identical to the expected value of the Y output that I actually want to estimate. So this is going to be an unbiased estimator of Y. So by estimating Z, I am effectively estimating Y. So then the question is, how do I set this C to guarantee that my Z estimator is going to have the reduced variance as possible? So how do I best design C to reduce the variance in Z relative to the variance in Y? And if you do a little calculus like we did last time, you find out that the optimal value for this C scalar is just the covariance between X and Y, which is a statistical quantity related to correlation that you can measure, divided by the variance in X. And so you can measure the variance in X, you can measure the variance in across all the different replications. You can say, for this replication, we got a high average, for this replication, we got a low average. You take all those averages, you can measure their variance. So you've got the variation in X. And then for each replication, you can see how correlated. You can do a scatter plot of all of the X values and all the Y values, and then use that correlation line to calculate covariance. And if you divide the covariance by the variance, you end up getting the optimal value for this scalar, which tells you the optimal way that you should subtract off your good luck, bad luck estimate from the actual measured performance variable that you found. And so by doing that, I get this estimator right here. And if I rewrite this just a little bit, it might provide more interpretation here. And so this is the exact same thing, but I've taken the variance and I've split it up into two standard deviations. And so what I end up finding here is that what I'm effectively doing is taking a standardized score of how my input varies. And so basically I'm saying, is this a good input and how good of an input it is? Is this a bad input and how bad of an input it is? So I'm effectively assigning a Z-score to every input that comes into every single replication. And I am taking that Z-score and I am then scaling it by this relationship here. in order to then figure out whether I need to decrease or increase my actual performance variable to account for whether I'm getting bad luck right now or good luck. So if I get a bad luck one, I'm going to increase the performance variable to say my performance is going to be too low because I was just got bad luck in my input. If I get good luck, I'm going to say my performance for this replication is going to be too high because I just had good luck in my input. So I'm going to bring it down. And so that gradually is going to reduce the variance in the output so we can get a better estimate with fewer replications for this absolute performance estimation. And so that's just all that we're doing there in this process. And so that's going to give us a table. And that table is going to have for every replication, it'll have a measure of our input. We know the average input, so we can even take summary statistics here. And we can use this average, this variance, and this covariance. We can use those to then calculate our control variates after the experiment is done. So you don't have to modify the experiment to do this. And so these were our original output measures. And then these are the modified measures here using that formula. And if I estimate the confidence interval for this thing, it will end up having a tighter variance than the confidence interval for this thing. And yet they both will be unbiased. And so this confidence interval will be a better estimator of the performance of this system than this confidence interval because it will have a tighter variance. And so it'll have a tighter confidence interval. So it'll be a more sensitive estimate. And so if I've done that as an example, and I just, when I ran the numbers for this particular example, this is just an example of what I end up getting. So for this output measure, I got an insignificant confidence interval. So if I am comparing this to 0 to say, is this significantly different from 0? This confidence interval, I can't tell the difference. I have no idea. There's just not enough data for me to discriminate between the output of this simulation and 0. But I take the exact same data and by controlling for the variance in my input and generating these new control variates, taking its confidence interval here, I see clearly is separated from 0. And so I know that in this one, I actually do have that this one is less than 0.05. And so this one is significantly different from 0. And so I can conclude that this performance, this absolute performance is guaranteed to be positive, basically, is what I come up from this. It's actually guaranteed to be greater than 3, but it's definitely guaranteed to be greater than 0 if 0 was our focus here. Whereas the original one that I got before I modified the outputs, I can't tell anything from. So that is control variates, and that's the last variance reduction technique that we go over in the class here. So are there any questions of that? Is that pretty clear? And again, this is an approach you can apply to any experiment that you run as an industrial engineer, not just a simulation experiment. Okay. All right, well, I don't have much more for you here in the last couple of minutes. So let's do an attendance response. And I might do one more attendance response. So there, it's in the chat. The link is in the chat. You can also get it from the screen here. And so the question I'm asking is, of the 4 variance reduction techniques that we've gone over, which of those 4 is built to purposely bias the inputs to greatly increase the number of normally rare output events? So what variance reduction technique is associated with amplifying rare events? So go ahead and put your answer there. Okay. All right. All right, so in the last couple slides, this is just kind of big picture course wrap-up stuff. So, just as a reminder, we have been primarily talking about discrete event system simulation down here, process-centric simulation. There are three major types of simulations that you'll see if you move on in simulation. Agent-based modeling, which we talked a little bit about this semester. There are other courses, it's used a lot in social science. And so here at ASU, there are some courses offered actually in sustainability by a guy named Marco Jansen, who go into agent-based modeling. Occasionally you'll see workshops on agent-based modeling. There's system dynamics modeling, which is the main focus of IEE 477. I also teach system dynamics modeling in a sustainability course, 212, that I teach next semester. And then there's, again, this class in 475. Within the three major simulation methodologies, there are a huge number of simulation platforms. You, of course, have been working primarily with Arena this semester. Arena is not the prettiest of programs. I understand that. It is a very traditional program that's out there. It is well known. Rockwell Automation makes a lot of money off of selling Arena to industry. So if you go into simulation in industrial engineering, you'll probably see Arena again. But some of you might see Semio. The people who built Arena started, spun off and built a new simulation platform called Semio, which basically is like Arena Part 2. Like, they basically rebuilt Arena from the ground up. It looks just like Arena, it operates a lot like Arena, but it has some significant differences. But if you know how to use Arena, you're gonna know how to use Semio. Similar to a bunch of other ones of these, like FlexSim, for example. So some of these do more than just discrete event system simulation. AnyLogic, which is used in 477, does all three simulation together. Some don't do any of these. And so, for example, VinSim focuses entirely on system dynamics modeling, the subject of 477. It doesn't really do discrete event system simulation, at least not on purpose. NetLogo really is just agent-based modeling. So a bunch of different platforms. Which one's right for you is going to kind of depend on a lot of different things. It's going to depend on your stakeholders, how attractive things are. Do they really want visualization? Do your stakeholders want to be able to use your simulation afterwards? Maybe an Excel spreadsheet is the best way for some stakeholders to really get in touch with your simulation. I'm not saying any one of these is better than others. We made one choice for this course, Arena, and a little bit of NetLogo. But I'm not saying that, I don't want you to think of this as the Arena course. We had to choose something. I want you to think of this as the discrete event system simulation course. And when you go off and you start working for Gore or whoever else makes you use simulation, then hopefully you'll be able to transport the things you've learned about Arena into those other simulation platforms. So that's kind of the big goal here. And there are, general processes that I'm hoping that you saw kind of being picked up here, from problem formulation to setting your objectives, to gathering data and conceptualizing your model, to turning your model into your first simulation model, to then trying to verify that your simulation model meets your conceptual model, and then validate that it actually looks like the real world, to then designing an experiment using your model as a surrogate for the real world, analyzing the output, reporting on that, and then maybe implementing out in the real world. This general flow chart is one that you'll use regardless of simulation platform. This is the process of simulation science, really, is all of this. And there's probably a loop that I have, in all science, there's a loop. You're going to implement something and it's going to work kind of well, but it won't quite work exactly as well as you might think. You'll realize that you left something out of your simulation. So then you form a new problem, which is, what's the missing component? And you'll generate hypotheses about that, which will cause you to generate new simulations and to do new tests. Models after models after models. That's really what this is all about. And your big question you should always be asking is the model that you're building illuminating and useful? It's never about accuracy. It's about, did I gain insights that allowed me to do something more useful in the world tomorrow than I could have done today? And that's kind of the big point of this course. So just put this up here, the timeline moving forward. This is the same thing that I mentioned before. Course evaluations are out. Our next lecture is just a review lecture. Make sure to give the ICA-MB a shot. beforehand so that you've got some good questions for me. Otherwise, I've got some canned lecture slides I can go through just like before. Presentations are going to be due next week. So just make sure that you've got yours turned in on Canvas by Wednesday so they can be peer reviewed by Saturday. And with that, I think we're at the end here. So I will do a closing attendance question, and I'm happy to chat for a few minutes about questions. The attendance quiz, the attendance question link is in there, and the question is on the slide there. Do you feel well prepared for your final project presentation? You can just give me a yes or no answer in your attendance response, and it's always interesting for me to review those. So without that, that's all I've got for you today. I'm at 11:46. If you have to go, you can feel free to take off. If you've got a couple of quick questions, I'm happy to stick around. So any questions?
So is the exam open for 24 hours on the dates for both phases?
Good question. So whatever group that you sign up to, early or late, for your group, you'll have access to the exams at the hours that I'm about to say, only during that. So if you sign up for the Monday, Tuesday group, you get no access on Thursday, Friday. If you sign up for the Thursday, Friday group, you get no access on Monday, Tuesday. The Thursday group, it'll be just like the midterm, where at midnight that night, it opens up for 24 hours. And anytime during that 24 hours, you get 90 minutes that you choose. Once you start, the clock starts ticking. And then after 90 minutes, your access gets closed off. And you have to then take it with Respondus Lockdown Browser plus Monitor. For the Friday, you just get all 24 hours and you get unlimited time. So for the 20% group one, you can, everybody's already seen the exam there. And so you can say, hey, I really had trouble with problem 5. Did anybody else have trouble with problem 5? Can anybody explain that? Maybe let's talk that through. Take as much time as you want, and then you all could agree on your answer to problem 5, and then you can all go back to your respective ones and put in your new answer for problem 5. And you'll have 24 hours, there's no 90-minute time limit in that second group. Does that make sense?
Yes, I just noticed that the deadline for the exam was set to like 11:45 a.m. So I just wasn't sure if it was open for 24 hours or if it was like we had to start at class time and then finish at the end of class time sort of thing.
Yeah, I haven't generated the exam yet, and because I haven't generated all the exam groups, the due dates and the exam periods are not quite set properly yet. So, that'll hopefully get fixed soon, and then once I can assign you into your sections, then the due dates will move according to whatever section you signed up for.
Okay, yeah, just making sure because I have a exam before it and after this class, so I have to figure my schedule out.
Sounds good. There was a private question in the chat. How do you switch your group? I'm in the early but want to take it late. If you go onto Canvas, go down the left-hand side and click on People. And then after you click on People, then there should be a tab. So, and I'll just put this in here, click on People in Canvas, and then 2, click on the Groups tab within the People area on Canvas. And then you should see groups. You'll probably see your lab group in there, and there should be a group that says early exam group and late exam group. And you should be able to click on the late exam group and say join, and it'll move you out of the early exam group into the late exam group. I know it seems to be working because some people have already done it. You'll also be able to view who's in those groups in case that helps change your mind about who you want to collaborate with. All right, any other questions?
Hi, Professor.
Yeah.
Yeah, I just wanted to ask, you might have mentioned this, but once we take the first exam, are we going to be able to see the score that we got?
You'll see the score. I think you'll see this. I'm pretty sure that, so I'm going to configure it so that you won't be able to see the correct answers until after everyone's done with the exam. So it'll be in the middle of the original finals week. I think it'll still tell you your score though, but there won't be a solution set available and you won't get the per question scores until after everyone's done.
Okay, thank you.
Any other questions? All right, so in that case, I hope everyone has a wonderful holiday, and looking forward to see you on Tuesday with your questions so we can talk about the final exam.